Alright, this is section 5.3, the definite interval. And so what we did last time is we said we could find the area, the accumulated distance, say for a particular time, by Riemann sums. Riemann sum says get all of these rectangles here and find the area of each rectangle. Well, how you find the area of the rectangle is you take the height, so that height would be evaluating at that particular, let's just call it x1, and then times the width, which is this change in x. And so Riemann sums said just sum all of those, find the areas for each one of those. And we said, okay, that's all and fine, but there's got to be an easier way, and there is, which is finding this total perfect area, so we don't have to worry about under or over estimates. We can find this by what's called integration, which says that we can find the limit, okay, so we can take the limit of the number of rectangles and we let that go to infinity. In other words, I have an infinite number of rectangles here, and I make the distance, the width, become 0. In other words, they get so close together that they're basically just a straight line of rectangles. And how I find that area is with what's called integration. These values here, as you can see from here, are just simply the interval that I'm interested in, and we typically call those my limits of integration. But that, as you can see, that shows my actual interval length. Alright, so if I want to estimate the area under this curve for this function from 0 to 3. In other words, what I want to do is I want to find this area, because that would give me my How do we do that? Well, for right now, we're just going to use technology, and you can find many websites out there that will find area under a curve by simply putting in this function and putting in my limits of integration, my interval, and you'll get this value. So this value here is that if I took all these rectangles here, found areas, and added them, summed them all up, and I let the number of rectangles go to infinity, I let their width go to 0, then this is the area that I would get. If I have a negative function, meaning that it's under the x-axis, I still can do the same thing. You just have to be careful, because like technology will just give you a negative value. And so all you would do then is just take the absolute value, because area is actually positive. So I would put this in that program. I'd put my limits -1 to 1, and I would get this value, and I would just rewrite it as an area of 1.3. How that can get you into trouble is if you have a positive area and a negative area, because what will happen is if you just do this in one swoop, you'll end up with subtracting this out. So what you have to do is, so find where the function equals 0. In other words, set the function equal to 0 and solve for x, and use that to subdivide your domain, and then find the integral of each subinterval, the area, by integrating it, and then add all of the areas up, but they're absolute, meaning that I find this 2.38. How do I find 2.38? I set this function equal to 0, and I solve this function for x. So as you can see, you could factor out an x, you'll end up with a square function, quadratic function that you could use quadratic formula, but that's how you would get that value. You set your function equal to 0, and it would tell you, because your function, if your function's at 0, you're right there. And so then I subdivide this and I say, okay, I'll just find this area, and then I'll find this area, and I'll absolute value this one, and then add them together. So notice now my intervals become 0 to 2.38, that's this piece, and then from 2.38 to 4, and that's that piece. So all I did was just split up my interval into two different intervals. I get this value, and as you see, I get a negative area for here. Well, all I have to do is absolute value that and then add, and I get the total area of 12.7. If you didn't do that, if you use that program and you just did from 0 to 4, you get a way different number than that 12 because you ended up subtracting this area out. And so you just have to be careful when you have a negative area that you take absolute area. If I want to calculate area between curves, in other words, I want to know what that area is. Well, if you just kind of look at this, you could see, what if I found this total area, and then what if I found the area under this curve and I subtracted that out? Okay, would make sense. And how I could find where that's going to happen, I can look at this intersection point. How do we know where two functions intersect? We set them equal to each other. If I find where the graph intersects, it will give me my range of integration. Okay, so that part's important. I need this. Okay, so as you can see, once I get where they actually intersect, then I can say, well, now I can find the area of the 4x minus x squared, which is this whole thing, and do it from 0 to 3.12, and then subtract what's under this curve, which is this one right here. Once again, you put this into the website and you get your actual area. Alright, so that's section 5.3. We're going to get to the point where you're not going to put things into a computer, you're going to actually calculate them. So this is the first step to that. We're not quite there yet, but section 5.4 is the interpretation of an integral. So this says the unit of measure for this integral from a to b of this function is the product of the units for f of x and the units for x. So if I have a function, r of t represents the rate at which the heart is pumping blood in liters per second, and t is time in seconds, give the units and the meaning of the following. So in other words, saying that this integral will represent the total amount of blood in liters pumped by the heart between 0 and 10 seconds. And so it gives me an actual rate of change, okay? So this f of t right here is my rate of change. So remember, that's the derivative, and what we're going to try to do here in a little bit is find the antiderivative. And so if I'm looking at this and say, well, the change in my position function, in other words, the change in the distance that we did last week, is the integral of the velocity, okay, of my derivative, or my rate of change. So what this means is if I had the original function, this is the derivative, if I could work backwards and get the original function, then I could just evaluate the original function from 0 to 30, and that would tell me my change in position. This is what we talked about, which is the fundamental theorem of calculus, how these are connected to each other, how derivatives and the original function are connected, and to be able to find these. Alright, in pharmacology, the definite integral is used to measure bioavailability, the overall presence of a drug in the bloodstream during the course of a treatment. A unit bioavailability represents 1 unit concentration of the drug in the blood hour. If we have a concentration of 3 milligrams per cubic centimeters in the blood for 2 hours, then we can estimate the bioavailability just simply by taking the concentration times the number of hours. So this was my concentration of a drug curve, okay, that we did a couple of weeks ago. And this makes sense because if you have a drug, it goes straight into the bloodstream and increases, okay, till it finally hits a maximum. And then hopefully it's starting to break down and go out of your system. So what would be better to do is to figure out a way, instead of estimating, because let's say we want to calculate the bioavailability of a drug that is in the blood with this concentration at time t from 0 to any we want. Well, over a small interval, there would be nothing wrong with estimating like we just did, okay? But an interval, what would be better, instead of doing rectangles and summing all of the rectangles, is we could actually integrate, meaning we could find the area underneath this curve. And so if we took the limit of that Riemann sums and we found this area, it would give us an exact. All right, that is the end of that section. So now we're going to jump to Chapter 7, Section 1. Okay, so this is constructing antiderivatives. For some of you that may have had this already in high school, you probably already know these little shortcuts for this. But what I'm going to do is for those of you that have never had this, we're going to try to figure out how these antiderivatives. So what is an antiderivative? If we have a function and we take its derivative, remember, as we've said before, that's still a function. And so if I take the derivative of my function, I get an actual function. With the antiderivative is we're working backwards. We're saying, I know the rate that something's changing. I know how the population is changing in San Antonio. I want to find the original function, okay, for many reasons. One of probably the most is for prediction. If I can find this original function, then I can reuse it. So again, working backwards. Well, I'm going to just flat out tell you x squared is an antiderivative of 2x. But the problem is there are other functions that also have the derivative of 2x. If I have these and I take the derivative, if I take the derivative of x squared, I get 2x plus a constant, take the derivative of the constant, that equals 0, so that goes away. If I take the derivative here, I get just 2x, but sometimes these constants are very important. Maybe this is adding another, drug into the system. Maybe this is taking it out. So these are things we need. We need to know these constants. Do that when we do antiderivatives is we call it a family of antiderivatives for any constant. And we just write plus c. So we can say that x squared plus c is a derivative of 2x. So let's see if we can figure out a pattern of how to find these antiderivatives. So an antiderivative of x is x squared over 2. You check it. Take this derivative. Remember, we're working backwards. We are given this, and we need to figure this piece out. Well, again, right now, I'm just kind of telling you. So how could we check it? We'll take the derivative. The 2 comes down. We end up canceling that, and sure enough, we get x. We can see a pattern. An antiderivative of x squared is x cubed over 3. True. Check it. Take the derivative of it and see, do you get x squared again? An antiderivative of x cubed is x to the 4th over 4. It looks like 4 comes down, 4's cancel, and I get x cubed. From all of these, you can look at this and hopefully you kind of recognize a pattern. Is if this is to the first power, it looks like I'm adding 1 to my exponent, and then whatever my exponent is comes down in the denominator. The definition of finding, for the power rule, for finding the antiderivative of a power is I add 1 to the exponent, and whatever that becomes also becomes my denominator, and again, because of the family of functions, also plus c. When I deal with constants, we just like to pull that constant out, and so finding the antiderivative, in other words, if I have a 1, how did I get a 1? Well, I started out with an x, because if I take x, I get 1. So the antiderivative of 3 dx is 3x, because the derivative of 3x gives me 3. So again, you're thinking backwards. These are just properties that some of us like to break our functions down into pieces, saying that if we want to find the integral of 2 functions added together, we actually could find the integral of the first one and then the integral of the second one and add or subtract them. Here, if you have a constant in front of a function, pull the constant out and just take the derivative of your actual function. So that's all. So let's go through a couple of examples. So for the first one, let's go ahead and break this into pieces, meaning I would rewrite this as 3x dx and x squared dx. Remember that dx, because a lot of times students will ask, what in the world is the dx? That's my change in x. Remember, we went from a Riemann sum that said I find, let's call that sub 1. How do I find the area under a curve? Riemann sum says you sum all of the areas of each rectangle, the height times the width. So that's all that piece is right there, is that's your width. And then we just, when we took the limit and we went to integrals, we just changed it to dx. All right, so going back to my definitions, I can bring that 3 out front, so I just have x dx and then plus this one. So my definition said when I find the antiderivative, I take the power and I add 1, and I do the same thing in the denominator. So I take the power, I add 1, and I do the same thing in the denominator. So I'm going to end up with 3x squared over 2 plus x cubed over 3, and don't forget that plus c. If you're not sure of your answer, take the derivative of it. If I take the derivative of this, I bring the 2 down so the 2's cancel and I end up with just 3x. If I take the derivative of this one, the 3 comes down, the 3's cancel, I subtract 1, and I end up with x squared. So it's kind of nice. You can take your answer and go back and actually check it, remembering this is the derivative and this is the original. All right, let's try another without having to break it down. So this, if I use my power rule, says add 1 and make that also my denominator. My power rule, add 1, also make that my denominator. And so I can just make this look a little bit better. Minus 2q to the 3rd power. And then, of course, plus c. Again, you're not sure if that's correct, check it. Take the derivative of it, and you should get that back. All right, here's some more definitions. If you think about it, if we took the derivative of ln of x, it was 1 over x, right? So there's the derivative. So working backwards, if I wanted to find the antiderivative of 1 over x, then it would be ln of x. The antiderivative of e to the x, so nice, e to the x is e to the x, whether you're doing derivatives or antiderivatives. And then this is that e to the kt, we just had it with time. And so the antiderivative of it would be 1 over whatever the value of k is, and then leave e to the kx in this case alone. So if I have this example, then I know the first piece is 8x to the 3rd over 3. Okay, because we just did these, that was the power. This, by that definition, then, is just simply ln of x. And the absolute value is hopefully you remember what a log function looks like, that your x's have to be positive. And that's it. That's your answer. If I have this and I'm looking over here, I would put that 12 out front, and then I would write this as 1 over 0.2, and then e to the 0.2t. And of course I certainly can divide that and get 60 e to the 0.2t plus c. So right now you're just simply looking at these definitions. I can also do trig functions, find antiderivatives for sines and cosines. So the antiderivative of the cosine is the sine. The antiderivative of the sine is the cosine. Well, think about this. If you're working back this way, what was the derivative of the sine? The cosine. If you're working back this way, what was the derivative of the cosine? It was the minus sign, so we need that negative and a negative to become our positive. And then here's our little chain rule pieces. Okay, so as you were doing the chain rule, how we would do these is simply whatever is inside becomes 1 over the constant that's on my variable, and then this stays the same, except of course cosine becomes. So if I have something like this, then from the definition, my sine is minus cosine of x. I'm going to throw that 3 out front. We just said by my definition up here, that's going to be 1 over 5, the cosine sine plus c. And so again, how could you check it? You could take the derivative of this and you should get that back.